Hey everybody, and welcome to what will probably be our last lecture in statistics. We should have two more lectures after this one, but this will be our last lecture in statistics. And today we're going to be talking about a normal distribution. As motivation for this, I'm going to go back to my two classes that we've been talking about in previous lectures. The first class, the final exam grades for all 10 students was 70. Every single student in the class, all 10 of them, got a 70 on their final exam. The mean X bar is 70. Everybody got a 70. The mean is 70. The percentage of scores in the class that's equal to 70, 100%. 100% of the scores in the class were equal to 70. Now that's not what we would consider normal. But let's just consider the ranges that the test scores could have fallen into. For example, percentage of test scores that are greater than or equal to 60 and less than or equal to 80. Well, in this case, it's still 100%. All of the test scores, all 10 of them equal 70. And all 10 of the test scores fell between 60 and 80. 100% of the class scored between 60 and 80. That's still unusual. Now let's do this interval. What percentage of the test scores fell between 50 and 90? Still 100%. And percentage of scores that fell between 40 and 100? 100%. This was a very unusual class. I would say that the test scores of this class are not normally distributed, whatever that means. Now, for the sake of comparison, let's look at my second class and their final exam scores. Yeah, let's look at our second class and their final exam grades. If you remember, we had 1, 2, 3, 4, 5, 6, 7 100s and 1, 2, 3 zeros. And the mean turned out to be 70%. That was what we call the class average. Now, of these 10 scores, what percentage of the scores actually equal the mean? Well, I don't actually see 70 up here anywhere, do I? So I guess I would say 0% of the test scores equal the mean. And that's not too surprising. Just because the class average was equal to 70 doesn't mean that we actually had to have anybody get 70. But if the class average turned out to be 70, we'd expect a lot of grades to be close to the mean, 70. So let's look at this. What about the percentage of test scores that are between 60 and 80? We'd expect a fair number to be between 60 and 80. All of these scores are either above 80 or below 60. Wow. So even though the mean is 70, none of the test scores are between 60 and 80. None of these test scores are real close to the mean, 70. This is kind of surprising. We would expect a lot of tests to be within 10 percentage points of the average, don't you think? Well, let's just expand the range a little bit more. What percentage of the test scores are between 50 and 90? That's 20 points either way from the mean of 70. What percentage of our test scores are between 50 and 90? If we look up here, none. Well, this is really weird. We have a class average of 70, and yet not a single person in the class scored within 20 points of our mean. 70 minus 20 is 50. 70 plus 20 is 90. Not a single person in the class came within 20 points of the mean. Well, I'm going to widen the category again. The percentage of scores between 40 and 100. Now, 40 is 30 points below the mean. 100 is 30 points above the mean. And we would think surely we'd have a bunch of people scoring within 30 points of the mean either way. And we do have some. All of these 100s, 7 of them, are within 30 points of the mean. They're in this category. 7 out of 10, that's 70%. This is about as abnormal a distribution of test grades as the first class. We have a class average or mean of 70, and yet not a single person scored within 10 points of the class average. That's weird. What's even weirder is that not a single person scored within 20 points either way of the mean. 70 minus 20 is 50. 70 plus 20 is 90. Not a single person in this class, 0%, scored within 20 points of the mean either way. And then when we opened up the category even further and had the interval of 30 points below the mean and 30 points above the mean, only 70% of the class had a test score in this interval. This is also an abnormal distribution of test grades. Neither of these classes had a distribution of grades that we would think was normal, so to speak. So let's remember these examples, and let's look at a fictitious class. I'll call it my third class. And this class is going to have more than 10 students. It's going to have 100 students. But let's see how my third class, a really, really normal class of students, let's see how they did on their final exam grades. Okay, this is my third class. And this third class it doesn't have just 10 students, it has 100 students in it. This class has so many students in it, I can't write all their test grades down on the board. But I know the numbers of the test grades that fell within each of these categories. Out of my 100 students, oh, by the way, this third class, you guessed it, the class average, the mean was 70 for this class also. But this class, it's not abnormal like the first class and the second class. This class, 100 students, by and large, they did what we'd expect a class of 100 students to do. They did what we'd expect a class of 100 normal students to do, or maybe I should say, they did what we'd expect a normal class of 100 students to do. The mean was 70, that's the class average, and the percentage of students in the class that got a 70, 5%. Out of 100 students, 5 of them actually got exactly the mean score or the average score. It's not shocking. We'd expect something like that. In 100 students, we'd expect maybe 2, 3, 5, 6, 7 to get about the class average. Now, the percentage of students who got between 60 and 80 in this class, (68%). My class has 100 students, and 68 of those students got between 60 and 80. And that makes sense. We'd expect most of the class to get test grades that were fairly close to the class average. This is 10 points below the class average. This is 10 points above the class average. The class average is 70. So this is 10 points below the class average. This is 10 points above the class average. And we'd expect a lot of students to be fairly close to the mean. And 68 of my 100 students were within 10 points of the class average one way or another. And let's say that we take a second category. We widen the category by 10 more points. So we have all the students who scored between 50 and 90. 50 is 20 points below the class average. 90 is 20 points above the class average. So we're looking at the percentage of students who got within 20 points of the class average one way or the other. Within 20 points of the mean one way or another. You know what? (95% of them did. Out of my 100 students, 95 of my students got between 50 and 90. Between 20 points below and 20 points above the class average. Well, I haven't accounted for all of my students yet, but I've accounted for most of them. And in this class, they did pretty much what we'd expect. Now I'm going to widen the category a little bit. I'm going to go 30 points below the class average. The class average, the mean is 70. I'm going to go 30 points below that, and I'm going to go 30 points above that. The percentage of scores that were between 40 and 100, (99%). All of my 100 students except for one got within 30 points either way of the class average. And that makes sense. This other person Well, you can't get any higher than 100, so I guess they got less than 40. Maybe they got a 0. Who knows? I hope not. But the test scores in this class are pretty much what we'd expect from a class. We look at the distribution of grades in this class. 68% got within 10 points of the class average. That sounds about right. 95% of the class got within 20 points of the class average. That sounds about right. Almost 100% got within 30 points of the class average. That sounds about right. We would say these test scores are normally distributed. We'd see this distribution of test scores and think, yeah, that sounds about right. Now, I'll tell you something. I use the term normally distributed because this looks like what we might normally expect to happen. It turns out that in statistics, the expression normally distributed and the expression normal distribution have a very specific meaning. And in part, the phrases normally distributed and normal distribution are appropriate because they accurately predict what will happen with most data values that we encounter. Most things in nature, a lot of things in experimentation, scientific studies, and so forth, are what we call normally distributed. Here, our test scores were normally distributed. The heights and weights of men and women, the heights and weights of teenage boys and girls, the heights and weights of pre-adolescent boys and girls, IQ scores, etc., etc. All of these things are normally distributed. If the average height for an adult American male is 5'10", we'd probably expect a large percentage of the population to be within 5'6" and 6'2", 4 inches either way. It wouldn't surprise us if a large percentage of American men, maybe 60, 70%, were within 4 inches of the mean height one way or another. If the mean height were 5'10", it wouldn't surprise us that 60, 70% of American men are between 5'6" and 6'2", 4 inches either way. It wouldn't surprise us that the vast majority of men were between 5'2" and 6'6". That's 8 inches either way from the mean. Wouldn't surprise us at all. And it wouldn't surprise us that almost 100% of adult American men are between 4'10" and 6'10". It would not surprise us. And in fact, data bears that this is essentially the case. Now, I'm making up the fact that, or I'm making up the figure that 5'10" is the average height for American men. It's probably like 5'9" something. And I'm using 4 inches as the distance one way or another for each category as I expand it. So that's probably not exactly right. But essentially, we should find the heights of adult American men distributed pretty much the way I described it. And we would say this is normally distributed, and it in fact follows the guidelines that are attributable to what we call a normal distribution. In statistics, normal distribution means something. And it has a little bit more meaning than what I've given here. Concerning the data values related to populations of living organisms, the vast majority of this data is modeled very well by what we call the normal distribution. And here we're going to say that our mean is X bar. In the future, if you actually do more statistics, you may see the mean represented by this figure. It's the lowercase Greek letter mu, mu. So the mean is X bar, or mu, and the standard deviation is S. The number of data values is evenly and symmetrically distributed about the mean X. 50% of the data values will be to the left of the mean. 50% of the data values will be to the right of the mean. And this distribution of data values will be symmetric. Notice the shape of this curve. If we folded it, if we drew a line right through the mean and took the right half and folded it over the mean, it would lie perfectly on top of the left half. There are some things to note. If we start at the mean X bar and we go a distance of 1 standard deviation to the right and a distance of 1 standard deviation to the left, the boundaries of this interval would be the mean X bar minus 1 standard deviation and the mean X bar plus 1 standard deviation. The number of data values of a normal distribution that lie within 1 standard deviation either way of the mean is going to be approximately 68%. Now, you know, in the last example, third class, the mean was 70. And 68 of those 100 students were within 10 points in either direction of the mean. They were between 60 and 80. Well, guess what? In that class, I guess 10 points was the standard deviation. So in our previous example, when we looked at the third class, and 68% of those students had test scores between 60 and 80, 60 and 80 represented the mean minus 1 standard deviation and the mean plus 1 standard deviation. And in that example, the standard deviation was 10 points. So for a data that's normally distributed, approximately 68% of the data values will be within 1 standard deviation either way of the mean X bar, or mu. Let's look at this normal distribution again. And this time, instead of going 1 standard deviation either way from the mean, we're going to go 2 standard deviations in each direction from the mean. We're going to start at the mean X bar and go 2 standard deviations to the left, and that will put us at X bar minus 2s. And we're going to start at the mean X bar and go 2 standard deviations to the right, That'll put us at x bar plus 2s. And notice the shaded portion of the graph now. Almost all of the area under the graph is shaded. A little bit more than 95% of the region under the graph and above the x-axis is shaded. And what this tells us is that 95% of the population, of a population that's normally distributed, lies between x minus 2 standard deviations and x plus 2 standard deviations. If we have a population that's normally distributed, approximately 95% of the data values will be between the mean minus 2 standard deviations and the mean plus 2 standard deviations. You know that class we were looking at, third class? See, 68% of the students were between 60 and 80. That's 1 standard deviation either way from the mean of 70. How many students were between 50 and 90? That's 2 standard deviations from the mean. We had 95 students that got between 50 and 90. Between 20 points either direction from the mean of 70. In our example, that meant that 95% of our students, or 95 of our students, got test scores that were within 2 standard deviations either direction of the mean. That class, I said it looked like a normal class, and it was. It had a standard deviation of 10, it had a mean of 70, and 95%, 95 students, had test scores that were within 2 standard deviations of the mean, one direction or another. The mean was 70, the mean minus 2 standard deviations was 50, the mean plus 2 standard deviations was 90. 95% of the test scores fell in that group. Now, let me tweak this graph just a little bit more. Hey everybody, here's this same normal distribution, except now we're going to start at the mean, x bar, and go 3 standard deviations to the right, and we're going to go 3 standard deviations to the left. And that takes us to the mean x bar plus 3 standard deviations, the mean x bar minus 3 standard deviations, and within this interval, x minus 3 standard deviations, x plus 3 standard deviations, 99.7% of the data values fall. Statisticians often say almost all data values. And when they say almost all, they're talking about between the mean minus 3 standard deviations and the mean plus 3 standard deviations. Within 3 standard deviations either way of the mean. Well, in my class, the third class that was normal in every respect, of those 100 students, how many of them got between 40 and 100? That's going to be 30 points either way from the mean. 99 of them did. And we're using a standard deviation of 10. So 40 was the mean 70 minus 3 standard deviations, and 100 was the mean 70 plus 3 standard deviations. And in that class, we had 99%. We couldn't have had 99.7%. We couldn't take that last student and cut them into two pieces, one of them being 7/10, the other one being 3/10, that other student just fell outside this interval somewhere. But in our class 3, the test scores were normally distributed. 99%, almost all of them, were within 3 standard deviations of the mean. 95% were within 2 standard deviations of the mean. And 68% were within 1 standard deviation of the mean. And this gives rise to our empirical rule, which I will write down in just a second. Here's our empirical rule. In any normal distribution of data, and this is important, the empirical rule only holds if our data is normally distributed. In any normal distribution of data, approximately 68% of all data lie within 1 standard deviation, either direction of the mean. So if we go 1 standard deviation to the left of the mean and 1 standard deviation to the right of the mean, we should encompass 68% of all data points. Approximately 95% of all data lie within 2 standard deviations, either direction of the mean. So if we start at the mean and we go to the left 2 standard deviations, and then we start at the mean and go 2 standard deviations to the right, between the mean minus 2 standard deviations and the mean plus 2 standard deviations, we should encompass 95% of all the data. And approximately 99.7% of all data will lie within 3 standard deviations, either direction of the mean. And sometimes we use the empirical rule just to make quick inferences about a population that's normally distributed. Or we may have a population and we're not sure if it's normally distributed or not. And we might see if the population has these characteristics. If it does, we can be pretty sure it's normally distributed. Now, there's something else that I should say about this empirical rule, and it has to do with the fact that when we looked at the graph of the normal distribution, the graph was symmetric about the mean. If we cut the graph in half with a vertical line going right through the mean, the left side of the graph would be the mirror image of the right side of the graph. And this symmetry can actually allow us to take the empirical rule a little bit further. Okay, let's see what implications we can draw from symmetry. Since the right half of the graph and the left half of the graph are exactly the same, they're mirror images of one another. Since it's true that 68% of all data lie within 1 standard deviation to the right or to the left of the mean, can we say that half that number, half of 68%, can we say that half that number, 34%, lie within 1 standard deviation to the right of the mean? Absolutely. The answer is unequivocally yes. Now, since the graph is symmetric, can I do this? And can I say half of this 68%, that is 34%, lie within 1 standard deviation to the left of the mean? And the answer again is absolutely yes. Can I do that with 2 standard deviations? "95% of all data lie within 2 standard deviations either way of the mean." 95% of all data lie within 2 standard deviations to the left or to the right of the mean. So can we take half of this 95%, which is 47.5%, and can we say half of this 95%, 47.5%, lie within 2 standard deviations to the right of the mean? Absolutely. The answer is absolutely yes. And therefore, could I also say instead that half of this 95%, 47.5%, lie within 2 standard deviations to the left of the mean? And again, the answer is absolutely yes. We can do that because the graph is symmetrical. And down here, could I take half of this 99.7? And what is that going to be? 49.85% of all data lie within 3 standard deviations to the right of the mean? Yep. And maybe I'll write that down. 49.85%. That's half of 99.7%. Can I say that 49.85% lie within 3 standard deviations to the right of the mean? Yep. Can I say that half of this, 49.85%, lie within 3 standard deviations to the left of the mean? Yep. So we should be alert to the fact that we can use the symmetry of the normal distribution in this way. Let's do a few examples with the empirical rule. I looked on the internet to try to find the actual mean height of adult American males and the standard deviation. And I got a lot of conflicting data. And so I'm just going to go with this. We'll suppose that the mean height of adult American males is 5'10", and that the standard deviation is 4 inches. What percentage of the population of adult males You know, one of these days I'm going to learn to speak English. What percentage of adult American males are between 5'2" and 6'6" in height? And it says assume normality. We'll assume that the heights of adult American males are normally distributed, and that's a valid assumption. In order to use the empirical rule, we're going to have to take these heights and compute them into the mean plus or minus a certain number of standard deviations. The mean is 5'10". So this is our mean, and we'll call it X bar, minus 5'2", Well, 5 feet minus 5 feet is 0. 10 inches minus 2 inches is 8 inches. Now, in terms of standard deviations, what is this? Standard deviation is 4 inches. So the difference of these is 2 standard deviations. Okay. Now, what about this? 6'6" minus the mean. And again, we're taking the difference of the x value. And you know what? Let's see. Tell you what, let me back up a bit and do this all over so that I can be a little bit more consistent. Here's what I'm going to do. I'm going to take the x value first, 5 foot 2 inches, and I'm going to subtract the mean, 5 foot 10 inches. X minus x bar (5 feet minus 5 feet is 0 feet. 2 inches minus 10 inches is negative 8 inches. And in terms of standard deviation, 4 inches, that's going to be negative 2x bar. And I did something else I'd like to apologize for here. I took the height x minus the mean height x bar and got negative 8 inches, and I want to write this in terms of standard deviations. And negative 8 inches is negative 2 times the standard deviation, 4 inches. But the standard deviation is S, isn't it? I had an X here or an X bar or something. S is the standard deviation. So my height, 5 foot 2, minus the mean height, 5 foot 10, is negative 8, and that's the same as negative 2 standard deviations. So this is what we have. X, the height, minus x bar, the mean height, is negative 2 standard deviations. And if I add x bar to both sides, I got x equals x bar minus 2 standard deviations. Okay. And my x value here is 5 foot 2. So the height, 5 foot 2, is the mean x bar minus 2 standard deviations. So what I've just established, this thing is x bar minus 2 standard deviations. I'm going to rewrite this height in terms of the mean and standard deviations also. Let's take the other height here, 6 foot 6, and write it in terms of standard deviations. We'll take the height, x equals 6 foot 6, and subtract the mean height, 5 foot 10, and we get 8 inches. See, if we add 8 inches to 5 foot 10, 2 of those inches will take us to 6 feet, and the other 6 will take us to 6 foot 6. So the height 6 foot 6 minus 5 foot 10 gives us 8 inches. And in terms of the standard deviation 4 inches, that's 2 standard deviations. So we have our height x minus the mean height x bar is 2 standard deviations. And if we add the mean height to both sides, we get x equals x bar plus 2 standard deviations. So in terms of mean and standard deviations, x, or 6 foot 10, is equal to the mean plus 2 standard deviations. So 6 foot 6, this is x bar plus 2 standard deviations. Now, what am I going to do with this? They ask us what percentage of the population of adult males are between 5 foot 2 and 6 foot 6 in height. That's the same thing as saying what percentage of the population of adult males is between the mean minus 2 standard deviations and the mean plus 2 standard deviations. In other words, they're saying what percentage of the population lies within 2 standard deviations either way of the mean. What percentage lies within 2 standard deviations either direction of the mean? The empirical rule tells us 95%. Okay, let's do one more using the empirical rule before we start working with tables. Okay, slightly different problem, same information. What percentage of the population of adult males are between 5 foot 2 and 6 foot 2 in height? And we'll assume normality. Again, we're going to have to take these measurements, 5 feet 2 inches and 6 feet 2 inches, and write them in terms of the mean and standard deviation. And when we did that before, we took our x value and subtracted the mean So here's x, and we're subtracting the mean, x bar. And that's going to give us -8 inches. And in terms of the standard deviation 4 inches, this is -2 times 4 inches. Now let's do the same thing for 6 foot 2. We'll take the x value, 6 foot 2, subtract x bar, 5 foot 10, here's our x value. Here's our mean x bar. And 6'2" minus 5'10", that's 4 inches. And that equals 1 times 4 inches. So that's 1 times our standard deviation, S. And my goodness. I'm going to have to clear out some more board space here. In our first case, forgive me, I'm going to have to erase this. In our first case, we have x minus x bar equal negative 2s, and that tells us x equals x bar minus 2s. We add x bar to both sides, and x is equal to x bar minus 2s. Now we also had 6'2" minus the mean 5'10" equal 4 inches, and that's 1 times s. And here we established that this x value minus the mean x bar is equal to 1s. And so x, if we add x bar to both sides, is the mean x bar plus 1s. And I'm going to rewrite this question in terms of the mean and standard deviation. What percentage of adult males are between 5'2" and 6'2" in height, but in terms of the mean and standard deviation, 5'2" is equal to x bar minus 2s. And you know what? Since I'm using x as 5'2" here, bear with me. I have x minus x bar equals negative 2s. So x equals x bar minus 2s. And here, our x is 5'2". 5'2" is x bar minus 2s. Down here, my x is 6'2", and I have my x 6'2" equals x bar plus 1s. So I could take this and write 6'2" is equal to x bar plus 1s. 5'2", x bar minus 2s, 6'2", x bar plus 1s. We want to know the percentage of population of adult males whose heights are between these two things. And let's look at the standard normal curve. One, two, here's the mean x bar. 1, 2, x bar plus 2s, x bar minus 2s, what percentage of the population is within 2 standard deviations of the mean x bar? 95%. Now, unfortunately, we're not going from x bar minus 2s to x bar plus 2s. We're going from x bar minus 2s to x bar plus 1s. So what I'm going to do is I'm going to go from x bar minus 2s to x bar. I'm going to take this half out completely. If we had 95% before, what are we going to have if we take away half of this curve? Take away half of the area under the curve. Won't that be half of 95%, which is 47.5%? So from x bar minus 2s to x bar, that's 47.5%. Now, let's pay attention to this x bar plus 1s. We'll look at the normal curve again. We'll look at the area between the mean minus 1 standard deviation and the mean plus 1 standard deviation. This was 68%, right? But what I want to do is I just want to look at the part from x bar to x bar plus s. So I'm going to take away half of the area under this curve. This was 68% when I had both sides, both parts filled. I took away half of that. What am I going to have now? 34%. And now I'm going to take both of these and put them together. I'm going to draw my curve again. Yikes, that's ugly. So here's one standard deviation, two standard deviations, one standard deviation, two standard deviations. And here's x bar, the mean, right in the middle. I want to go from x bar minus 2s, which is right here, to x bar plus s, which is right here. That area alone is 34%. This area is 47.5%. So what total percentage do we have from x bar minus 2s to x bar plus s? 47.5% plus 34%. 81.5%. So 81.5% are between 5'2" and 6'2". And in retrospect, notice how it was that we used symmetry here to get an answer when the region that we were working with wasn't centered about the mean. We had two standard deviations to the left of the mean and one standard deviation to the right of the mean. We used symmetry to get these percentages. This 47.5% is 1/2 of what we would have had if we went from x bar minus 2s to x bar plus 2s. This 34% is 1/2 of what we would have had if we went x bar minus s to x bar plus s. In other words, this 47.5% is 1/2 of what we would have had if we went two standard deviations either way from the mean. This 34% is 1/2 of what we would have had if we went one standard deviation either way of the mean. So we used the symmetry of the curve extensively.